In an unsteady open channel flow, velocity and depth change with time and position. The Saint-Venant equations constitute a system of two equations to solve one-dimensional unsteady open channel flow. A seminal application is a dam break wave. Let us consider the sudden release of a semi-infinite reservoir in a dry horizontal channel. While the ideal fluid flow solution was first solved in 1892, the experimental observation showed that the boundary friction significantly slowed down the propagation of the leading tip, and the leading tip is seen to have a rounded shape in comparison to the ideal fluid flow solution. The effect of flow resistance on the dam break wave were considered analytically by a number of researchers. A conceptual model was developed based upon the assumption that in the wave tip region, the resistant forces are exactly balanced by pressure forces, and the acceleration and inertial terms in the dynamic equation are therefore ignored. The simplified solution at the wave tip is combined with an inviscid dynamic wave solution away from the wave front. This schematic shows a longitudinal free surface profile at a time t after the dam break. The two regions are clearly highlighted, the wave tip region on the right hand side and the inviscid region or Ritter solution in the middle. In the wave tip, the flow resistance is dominant, the acceleration and initial terms are small, and assuming that the flow velocity does not vary rapidly in the leading tip and that it is equal to the wave front celerity, the dynamic equation may reduce in a diffusive wave equation, in which F is a Darcy-Weisbach friction factor. Assuming a constant friction factor, the equation of the diffusive wave equation gives the shape of the wave tip. The analytical solution has been successfully compared to a number of data, including tsunami front data on this graph. In the ideal fluid flow region, the flow properties are solved using the method of characteristic and simple wave. The complete solution, wave tip plus ideal fluid flow region, is solved ensuring the continuity of the depth and velocity at the transition between the ideal fluid flow and wave tip region, and the conservation of mass must be satisfied. The complete solution is a series of explicit equations. The first equation gives an explicit expression between the wave front celerity and the time t. The second gives the location of the leading edge of the dam break wave. The last three equations give the shape of the instantaneous dam break wave free surface profile at a time t. The complete solution is compared here to the ideal fluid flow solution and experimental data in a dimensionalized graph. The calculation were performed assuming F equals 0.03 and the experimental flow condition correspond to an initial reservoir of 0.074 meter, the data being recorded 9.4 seconds after the dam break. Some more advanced solution was developed assuming a non-constant friction coefficient. While more complicated, such a solution provided more detailed insight into the boundary shear stress in the leading tip region. Yet, overall there were negligible differences in terms of wave front celerity and instantaneous free surface profile, as well as good agreement with experimental data. This apparent contradiction may reflect upon our ignorance of some fundamental turbulent processes in the wave tip region. This sketch shows a difference in boundary shear stress between the solution with constant friction factor in the wave tip region, green line, Dressler approximation, dashed black line, and a solution of the Moody diagram for turbulent dam break wave in red. The Saint-Venant equation and dam break wave are essential concepts for the numerical modeling of open channel flow and its practical applications that are discussed in the relevant YouTube video movies in the same playlist.